was working here in SolidWorks technical support, as well as specialized expertise in our FEA, CFD, PDM, SolidWorks plastics, and all the various products. So here you all be here for to know how we can accelerate our performance with using our validation tools. So let's go upon with that. So basically I would like to interact with the design team. So the design team will perform their design once it completed. So we need to validate the design for that. So whether it is okay with respect to the self height, with respect to the gravity, with respect to motion, vibration, kind of such things, everything we need to come in to check with the before releasing our design. So for that, we offering the solutions called FEA solution we are having for volume, for fluid dynamics we are having, also for plastic injection. So first of all, we'll take it up with the short introduction of a simulation. So let's check with the designing a better frame. So you can see on the screen, I'm showing a tables. It was designed with using of square tubes in the weldment structures. So while I'm getting placing with this of 16,000 Newton, okay. Okay, with this we need to check with which is stronger and how much it is stronger. So before that, designer has designed with this left hand side of structure with which has no supports. So on the right hand side we can see the supports where in an angle of around some of 45 or 60 or something else. Okay, so we need to check before it goes to welding fabrication sectors. So for that, the designer has designed a material with the carbon steel and with 30 degree of angle placing and 45 degree of angle placing and 60 degree of placing. So for that we need to know that which one is best. So you can see after getting simulated, the simulated appearance of this will look like this. So you can see the color indicates the red, green, blue, and light blue something else, and green. Okay, with this we can't able to predict the value. So we need to check the value, how much the stresses has been induced in that particular places of highest stresses there. So we can compare that. Yeah, the deflection of this 30 degree is good, 80.86 mm, and the factor of safety is 2.8. For 45 degrees 0.71, yes, it is lesser, and the factor of safety is also getting lesser. So we doesn't mean that it is also in above 2 factor of safety. So this is the best design. You can see the deflection is also less and the factor of safety is more. So what we can conclude here is we need to have a better clarity on before releasing. For that we can have a solution, we can have an analysis validation before that. So for that we have a different type of scenarios. Okay, what I was said is before, the 3 angle of is better, best, and good. So this one is the 60 degree is the best frame for us. Okay, this is a sample scenario. So here I have a alternate development process of a serial process. Before that, end users what they were planning, and they will design a product in detail and validating technical communication and operation. So with how we propose, we will have our product management, a detailed product design and design simulation, technical communication. We offering more and more. So which will reduce your operation cost, which will reduce your material cost once you get into analysis, once you go to manufacturing. So I would suggest similar to design with this. Okay, for that we are offering a design validation called for FEA in simulation name, flow simulation, and the plastics. So we'll go with today's session with SolidWorks simulation. So after upcoming webinars, I will cover up with the set of studies goes to. So today I will get into our FEA. So we have, once again, yeah, on this we can see on the screen we'll offer the solutions called up to nonlinear dynamic analysis. So we can have a composite materials inbuilt inside in that also. So today's webinar I'm going to cover up with a starting of static analysis with motion analysis and a thermal kind of application oriented files I would like to share. Here I would like to show some of basic of the finding out of the static analysis. So what the static analysis will while we are performing, so we can find the maximum stress where it is happened in the entire structure, where we can analyze this for a particular part or assembly. So this will permit we can check with respect to the stresses how much the deformation is going to happen in our entire total assembly. So what is the benefit here? So with using this analysis, this is a basic initial analysis for our assembly. Assembly has some of the contacts will be there, some of bolt connections, some of the pin connections, spring connections, everything can be automatically imported with using our SolidWorks simulation tool. So this is the benefit, we can avoid a failure of the particular assembly. Okay, here on the screen I have opened a single cylinder four-stroke engine mechanisms set of demo set file with you. Okay, which contains files you can see, which is it is in a top level assembly. Transparency. Okay, transparent type of. So this is the casing of the bottom. Okay, I will show you with hiding that. The camshaft is inside. The piston connecting rod, piston ring is over there. So we need to check with the thermal, how much the temperature is dissipating, how much the stresses is going to be occur here, how the motion analysis is going to get our solution results here. So before that, I would like to activate the SolidWorks simulation and the motion analysis to find out the various results. Okay, for that I'm enabling a SolidWorks simulation as an add-in here on the command manager. Once it has been activated, what are all the studies we have performed will automatically shown over here. We doesn't need to go upon and open again for the files and all. So which the files, this assembly contains any of the static or thermal or any of study types, it will highlight it over here. The results will automatically load if we solved properly. Done. Okay, okay, we need to go for a motion analysis for this. Basically, okay, I'll cover up motion analysis later, and we can go with the static analysis first of all. So this is the static analysis structure on the left screen, where the parts contains a tree. This is the simulation tree. Here you can see, whereas these parts will be included in the model. Once I'm going with this new study with respect to static. Once I clicked OK, the new static study window will appear on the bottom. Okay, on the bottom pane. Now the static one, the study name we can also rename it here, where this symbol will indicate the static symbol. So this is the thermal, and this is also a static for the piston rings. So with this entire assembly, initially I would like to solve with whole assembly. For that, we need to import the material for this particular individual parts or solid bodies. If you solving any of the parts with multiple solid bodies, also can be provided with different materials also. Here you can see that the connecting rod material is T6SN, and the crankshaft material is 4340 ASI steel, and every material is different. So where it can be, so you can have this. If the material is same for all inside the assembly, we can go for all. If it is different, we can one second, single part, we can right click with respect to the connecting rod, right clicking the particular part, we can go for the material selection. This selection is available in our SolidWorks library itself. So we can also customize the materials with respect to the company standard. So we can have a custom material for this. So the custom material we can have. Okay, this applications, this every companies will have their own material specifications. For that we can have a custom material also. So for this material I can go up with the identical material inside for any of different material properties for that. Okay, okay, this is an assembly analysis. For that we need to have a local interaction for that contacts of every parts. So initially this assembly contains, there is a motion which contains there is a motion moment there. This is not a bonder, this is a contact phase. This cylindrical phase, piston phase or in contact. So for that we can have a contact phase for these two phases. How it is? Okay, here we can see the local interaction will looks like this. So the one set of phases which indicates in blue and another which indicates in pink. So this indicates the phase of the cylinder, and the top selected as a piston outer cylindrical phase. This is OD/ID. Okay. In case of any gap clearances, we can also mention it over there. So the software will automatically solve with respect to the gap clearance where we derive. Okay, the connecting at the next is connecting rod and the camshaft location. For that, the contact phases of the inner and the particular connecting part. This is the one thing, and respectively the everything is being in contact. Okay, so once we have done, we need to give a fixing part of area. So this is this assembly is getting fixed with the engine interior at this particular bottom of these areas, right? So for that we are going fixing with this, and this reference geometry which is allows where this is the reference geometry where the translation is arresting and which translation we are allowing. For that we can have this use advanced fixtures under we can have a reference geometry loads which is used for different applications. So if it is in a force, you can give a force, or if it is a pressure, you can give it for a pressure load, or there is a cylindrical shaft kind of such things we can derive with the torque loads, and it is a centrifugal in radians per second or something we can give. Any bearing load is getting occurred, we can give. Also temperature load is also available, and the remote load mass which is it is useful for a large assembly. If I want to analyze a large assembly, so none other I doesn't require entire assembly to be opened and meshed inside. So instead that the remote load or mass will act as a to reduce to increasing the solving time. We can have this remote loader mass on distributed mass. So this is the option, and we have, so instead I have placed a pin with camshaft connection also, and this is the physical part. So there is no virtual connections I have placed over here. So once it completed, what I need to do is I need to mesh the particular entire assembly. We can see the meshing how it is. Okay, fine. Once it mesh, let me hide this. Once it's done, after solving this analysis, find out the stresses. So once it derived with this load, we can have a stresses value. Okay, getting loaded. Okay, after solving this, we can find the maximum stresses where it is happened. Okay, let's see where it is. The 114 megapascal of the stress value has happened at that phases. I can see where it is. The maximum is at this area. Okay, this is how we can find. And not only the stresses value, we need to check with the displacement, how much the deformation is happened for the 1200 psi load I would derive. So displacement is, it is getting low. Okay, so it is 0.01 mm the deflection. This shows the section view of this entire assembly. You can see that the value which indicates the colors, this is the maximum from the top to bottom, and also we can animate the file. The display deformation scale is 1, and okay, it is great. Okay, this is how the displacement will occur. Okay, this is up to our static analysis, so I'll cover up with the thermal analysis. So where we can go for a new study, and we can select with the thermal analysis. The thermal study will open it over here. Here, what is the same procedure has been carried out here? The contacts and the loads only varying. The convection coefficient we need to derive for this. So the temperature of this hole at the top is 150 degrees Celsius value, where we can right click the thermal load, we can derive with temperature, convection, heat flux, heat power, and the radiation boundary conditions also. So in this scenario, what I have derived is, I go for the convection of this outer of the surface. The convection from the heat is generated inside, the convection is which comes at outer phases. So once it completed, simply I can go for mesh and I can run this study to get the thermal temperature results for this. So this is for, we can plot with multiple scenario for this file, or if I need to check for the ring everything also, we can go with ring temperature, or this is the cut section of this view where the 150 degrees Celsius is where, and the color indicates 149 simultaneously. So I can go for with ring as well. So where it is, I can go, I can click with results, define thermal plot. So for this particular solid bodies or particular solid rings, the parts contains. So here is the advanced options. Show plot only on the selected entities, which allows you to select the single part or dual part. Everything can be selected for. This plot has been generated with respect to that advanced option. So one scenario I need to check with that only piston. Okay, for that also we can have the same setups by excluding the analysis by simply right clicking and exclude, again solving, again fixing it at the bottom of this particular area, and here is the mesh control option we have by right clicking. Okay, this is the stress plot for this, and displacement plot we can check not only the resultant displacement, we can have y direction displacement how much, or x direction or z direction as well. So coming to at the last, previously I have covered with static and thermal with two type of iteration scenarios. So here is the motion analysis where I enable the motion analysis adding. I can have the motion analysis with the drop down. Previously it is animation and basic will be available. We can have the motion analysis for this as well. So for that, the time steps will be over up here. Okay, initially what we need to do, we can here is I would like to explain is the motor. What kind of a motor? It is a translation or rotational. We can define. Is there any spring kind of things? We can have a spring, damping, and the forces. So the forces, particularly how much the forces will be. So here is the forces, how much force is getting transferred here, and the contacts for the parts. So the contact for the parts, this and these are the contacts we can derive, and the gravity I can show. This is the after solving that. Before I would show the rotary motor, how much. This is the rotating region, and the phases, this is the rotating of a clockwise. Once the speed can be defined with constant speed or oscillator or data points or that some distance for that rotation. So here instantly 1000 rpm, so I have placed it over here. Once I've completed, simply what I need to do is I need to calculate for this, and also gravity included, and also force has been included for that. Okay, and the gravity with respect to the y direction, you can see here the arrow mark will define minus y direction. Once I've completed, I can simply calculate with the motion for 0.12 second. Okay, once I completed, I can plot the result with respect to the graph x and y plot. Okay, once I clicked here, what are all the results we can have? We can have the displacement velocity, acceleration forces, and the forces, which means in motor force, motor torque, and reaction force and moment friction force as well. And the contact force for the particular areas also we can plot it over for the forces. And the momentum, how much the translation momentum for this x magnitude part or y magnitude part, the kinetic energy, angular kinetic, total kinetic, everything can be derived. So for this scenario, one more other quantities, so the angle of the projection angle can be calculated out with respect to. So here I have plotted some of the results previously. How much the motor power consumption, what is the motor torque, and what is the acceleration versus angle. These are all the plots where I can have with the plot area. So what is the velocity, show plot. What is the velocity with respect to time? So this is the velocity plot, and this is the time plot. So at 0 seconds, at 0.02 seconds, the 2717 millimeter per second is the velocity for that. And constantly it is getting up. This is the plot. We can save as a save. We can export it as a CSV file. Everything can be done. And I can go for power consumption of the particular motion. Okay, in watts, power consumption for this seconds. At 0 second is the power consumption, and 1.1, 0.01 O2 up to 0.12. How much we have solved for the timestamps. And what is the torque for this? What is the torque at 0 second? At 2.12 is the torque. It is getting varied. And acceleration, and this is the acceleration, so where I can play. So you can simultaneously play with the graph. Okay, that's it about motion analysis, where the results can be plotted over here. Coming up with the end of the session.